Okay, let's unpack this. We've all heard ice crack. I mean, it's that, you know, gentle tink of an ice cube in your drink.
Right. Or the crunch of packed snow.
Exactly, that muffled crunch underfoot.
Mhm.
It's usually a pretty dull, almost passive sound. But what if I told you there's a kind of natural ice that when it breaks, it doesn't just crack, it actually sings?
It sings is a good way to put it.
Yeah, it releases this sound that's so sharp and intense that glaciologists have called it a small explosion, or, and get this, a deep, resonating laser beam.
That sounds completely fictional, right? Like something from a sci-fi movie set on a frozen planet. But this deep dive today is all about this very real, surprisingly loud physical thing.
People call it the sound of breaking ice.
And it is one of the most compelling acoustic events in the entire natural world.
So our mission here is to basically shortcut you to understanding the incredibly specific physics behind this sound, because this is not your ordinary frozen water. We are talking about highly specialized ice crystals and everything about them, how they form, how they're linked. It's all engineered by nature to turn a tiny fracture into this startling event.
Exactly. The magic, if you want to call it that, is all in the precision of the structure. And that precision, it demands absolute extremes in temperature.
Okay, so that's a perfect place to start. The conditions. What's the non-negotiable recipe for ice that whistles or bangs like this? What separates it from freezer ice?
It really is one key condition, temperature, and you can't overstate how cold it has to be. The research we looked at all points to the ice crystals having to form at temperatures that are hovering right around minus 40 degrees Celsius.
Minus 40. Wow.
That's the threshold.
So that kind of cold, it forces molecules to do pretty unusual things. Why is that specific deep cold so critical for the ice's structure?
Well, think about what happens when water freezes quickly, say, in your kitchen.
Okay.
That fast freezing traps air pockets, right? It creates these messy, kind of disorganized crystals. But at an ambient temperature of minus 40 Celsius, the whole freezing process is incredibly slow and constrained.
So it's more deliberate.
Very. It allows the water molecules to settle into an almost perfect hexagonal lattice structure.
So that slow, profound cold is creating purity and density.
Precisely. The studies show that the crystals that form are exceptionally small, incredibly precise in how they're aligned, and, this is the most important part, they are extremely tightly bound together.
They're not just touching.
No, not at all. They're under this immense, constant internal mechanical stress just by existing. They're basically storing up energy.
But wait, if it's just water freezing, why wouldn't, say, my local lake ice make this noise? I mean, it's also stressed by the cold. Is it just the scale, or is there something fundamentally different about those bonds at minus 40?
It's the difference between structured tension and messy freezing.
Messy freezing, I like that.
Yeah, your freezer ice has impurities, micro air pockets. Those things allow tiny little stress releases, those dull tinks, to just happen silently and dissipate.
Ah, so there's no buildup.
Exactly. In the minus 40-degree ice, there are virtually no imperfections. So all that stress just accumulates uniformly across this massive network of perfectly aligned bonds. When one bond fails, it's not a single crack, it's a catastrophic release just waiting to happen.
That stressed out, compressed structure, that leads us right into the core mechanism, right? How this stored energy gets released as sound.
This is where we have to talk about something called acoustic emission. It's the fundamental principle at play here.
Sure.
Because those crystals are so perfectly and tightly bound, all that enormous energy from their formation is essentially trapped. It's stored as elastic potential energy within that rigid structure.
So it's trapped energy just ready to go, and the fracture is the trigger.
Exactly right. When that structure is disturbed by weight, pressure, even a subtle temperature change, the sudden release of that highly stressed energy is what creates the initial sharp sound wave.
Okay.
We often use the analogy of breaking glass. When highly stressed glass shatters, it releases that energy instantly, creating that sharp, high-frequency sound. That is acoustic emission.
The glass analogy really helps grasp that initial ping. But, you know, broken glass, while it's sharp, you can't hear it a kilometer away.
Yeah.
So if acoustic emission is the mechanism, why does the sound escalate from just a sharp crack to something so much louder?
Yeah.
The glass analogy kind of falls apart when you talk about scale.
It does. It absolutely does. And that's because we have to introduce the real amplifier here. This is the second critical concept. The ice fracture cascade.
A cascade,
Okay,
okay.
yeah.
That suggests a chain reaction, which would definitely explain the amplification.
Precisely. Remember how I said every single ice crystal is tightly bound and under perfect stress?
Mm-hmm.
The difference here is that the crystals aren't just linked, they are structurally dependent on hundreds of their neighbors.
So when one crystal breaks, the load just immediately shifts to all the adjacent crystals, which are already at their breaking point.
That is the crucial detail. When an external force causes just one crystal bond to snap, it instantly triggers a chain reaction of mechanical failure. It is a literal domino effect.
Wow.
It causes all the other interconnected stressed crystals to fracture sequentially, one after the other, in incredibly rapid succession.
So fast it sounds synchronized.
Exactly. And that transforms that single, sharp ping of the acoustic emission into a massive, continuous wave of sound.
It's almost like a self-sustaining wave of destruction moving through the ice sheet itself.
That's a great way to put it. The sheer scale and speed of this fracturing is why the sound travels so far. Glaciologists in polar regions, they've recorded this sound from up to a kilometer away.
A full kilometer.
And the quality of the sound, that depends on the cascade. If it's quick and localized, you get that sharp laser-like zap. If the cascade moves across a vast area, you hear that longer, deeper resonance, the light muffled explosion.
It's the ice itself screaming as it adjusts.
Hmm.
That brings us to, I think, the most relatable part, the real-world experience.
Mhm.
So let's picture this. You're walking on a massive frozen lake. It's seriously cold, and suddenly you hear that loud crack, that full cascade, but it sounds like it's right under your feet, or maybe from some distant, untraceable spot.
That feeling is very real, and it's rooted in two things that kind of warp our perception of sound and distance on ice.
Your first thought is, I'm about to fall in.
Of course. But often, the actual fracture point is far away from you.
So why does the stress build up far away from where I'm standing?
Okay, think of the ice sheet like a massive, flexible trampoline. When you step on the middle, the greatest amount of tension is actually at the edges of the depression your weight is causing.
Oh, right.
Your pressure makes the sheet flex downward, and that creates these immense stress points in peripheral areas, maybe 50 or 100 meters away, where the ice might be thinner or already compromised. That's where the cascade starts.
So my foot is pushing down here, but the actual break is way over there where the sheet is bending the most. That explains the misdirection. But why does the sound feel instantaneous? Why does it get to me so quickly?
And that is the second really surprising factor, the speed of sound. We're used to hearing sound travel through air, which is relatively slow.
Right?
But the sound from that fracture reaches you almost instantly because it travels significantly faster inside the medium of the solid ice itself.
Ah, so the ice is its own super-fast highway for the sound waves.
Precisely. The speed of sound through a solid, like ice, is roughly 3, maybe 4 times faster than through cold air.
Wow.
So that immediate delivery, it cancels out the distance delay you'd normally expect, and that contributes to that unsettling feeling that the ground is groaning right beneath you, even if the break was 100 yards away.
It's the ice communicating its distress at incredible speed.
You could say that.
It really changes how you perceive what you think is a static environment.
Hmm.
We see these vast frozen landscapes as silent, white voids.
Yeah.
But they're constantly alive, transmitting massive amounts of energy through sound waves at high velocity. It's a dynamic acoustic landscape.
It raises a really important point about glaciology. We can't just study ice visually or chemically. We have to listen to it. The sounds tell us about internal stresses, the freezing rate, the condition of the crystal structure miles away.
That is a perfect synthesis of what we've covered. I mean, we started with a sound that seemed like it came from a sci-fi movie.
A ray gun, yeah.
And we've grounded it in some pretty profound physical principles.
So let's recap the 3 core takeaways for everyone listening. First, you absolutely need that extreme, specific cold.
That precise formation temperature, right around minus 40 degrees Celsius, that's what creates that dense, tightly bound, stressed out crystal structure.
Exactly. Second, the core mechanism for the sound is acoustic emission.
That's the sudden, sharp release of trapped energy when the bonds snap. The breaking glass analogy.
Right. And finally, the reason it gets so loud, the reason it goes from a ping to a roar, is the ice fracture cascade.
The instant rapid domino effect.